And good morning, everybody, or good afternoon, good evening, wherever you are on the globe. Welcome to the GeoSolutions webinar on building and consuming urban digital twins using open source tools. Today, you'll be joined by, or the presentation will be guided by Tobia DePisa, Stefano Bovio, and Georgios is also on the line with us today. So we'll do a brief introduction, introduce you to who GeoSolutions is, and then get started with the 3D urban digital twin presentation. There's been a lot of momentum around urban digital twins, especially in city planning, transportation, emergency management and response, et cetera. So there's a lot of excitement here. And we've been a Cesium 3D developer now for about a year as an organization. So I want to emphasize that we're always here to help you better understand or answer questions related to 3D tiles and any Cesium 3D work you might be doing. My name is Ryan Burley. I am in the US, and we have offices in Italy and the US. We've been focused on open source development for 17, 18 years now. For those of you not familiar with GeoSolutions, GeoSolutions employs a majority of the core code developers and core code committers for GeoServer, GeoNode, MapStore, GeoNetwork, and all of the associated plugins around GeoServer, right? And some of the underlying tool sets such as GeoTools, the OGC protocols, et cetera. So we're always or frequently asked, how do we make money? What's our business model? We provide professional training services. We do a lot of guaranteed or subscription services where we can host a GeoServer, for example, for your organization. We offer commercial support. If you ever need somebody as a reach back or a direct pipeline to the core code developers, we're always here to support you. And we do a lot of custom development as well. That being said, if you ever have any basic questions, or you just have some questions about getting GeoServer or MapStore or anything open source related, we're always here to help you out. Never hesitate to reach out. We have customers all over the globe, as you can see from this map, with a focus on several different industries. We're very industry agnostic. We work in all levels of government, military, commercial verticals such as telecom, research, Earth observation, obviously. And our key focus, I guess, our niche, if you will, or our specialty is getting massive amounts of data from sensors to end user applications. So there's the WebGIS, WebGIS performance between server and client applications, and then all of the data engineering around just getting data transmitted from sensors all the way through the plumbing, if you will, out to whatever the end user application you're using, leveraging open source software. We are members of OSGeo, OGC, United States Geospatial Intelligence Foundation. And as I mentioned previously, we are certified Cesium developers as an organization. So we do have a very high level of expertise in Cesium and 3D tile generation and how to implement that within your organization, leveraging open source. I do want to emphasize resources. There are plenty of videos. We have a blog on our website to keep apprised of what's going on in open source in the industry in general. This recording will be posted on our YouTube channel, which also has all of our past webinar recordings. Again, everything from GeoServer integration to GeoNode, latest release updates, MapStore. There's a full stack of videos available for you. If you're ever looking for anything specific, let us know. And again, if you ever have any questions, we're always interested in hearing how open source tools are being used out in the wild. And if you ever have any questions, feel free to reach out to me directly or info@geosolutionsgroup.com. And with that, I will pass it off to Tobia and Stefano. And we'll get started on building urban digital twins using open source tools. Take it away, guys.
Thank you so much, Ryan. Can you share the screen, Stefano, please? Okay, so first of all, I would like to present myself. So hi everyone. My name is Tobia Dipisa. I'm product owner of MapStore WebGIS at GeoSolutions. So in this webinar, we will, let's say, guide you in the process of transforming, as Ryan said, the vector data and point clouds datasets into 3D tiles format by using our product Digital Twin Toolbox. Okay, so you can skip to the first slide of the introduction, please. So consuming 3D data, let's say in a WebGIS application, in WebGIS applications, has increasingly become a requirement, no? Over the last years for many environments. So and fields, ranges of use, for example, such as digital twins and urban planning, flight operations, and aerospace in general, IoT real-time, underground, undersea, sea, and so on. So the urban environment is one of the main contexts in which many organizations, but also public administrations and, well, municipalities, actually have concrete needs to provide even more advanced 3D digital representations. So this subject usually have also to, let's say, combine existing 2D data within a 3D environment with a proper and reliable representation of terrain, buildings, urban features, etc. So in the overall picture, the 3D tiles become one of the main format for streaming and rendering 3D geospatial contents on the web. So as you can see from the slide, for LiDAR derived meshes, oblique imagery, 3D buildings, point clouds, and more. So please, the next. So, I mean, considering effectively the ever-growing and even more specific needs in that context, it is usually necessary to, first of all, identify the best tools for viewing 3D data in that format. And then, of course, identify tools to convert existing data sets into 3D tiles format in a proper and performing way. But of course, the question is, what about doing that using open source tools? So that's effectively was effectively the challenge for us. So of course, the answer to the first question is, I mean, quite immediate. Okay, so you can use MapStore, which is a performing WebGIS for visualizing, styling, measuring, browsing 3D data in such format. With many functionalities, many functions available out of the box. So please, the next. So for the second point, of course, there is the Digital Twin Toolbox, but the aim of the Digital Twin Toolbox is to effectively support with the conversion process to 3D tile format by using a well-driven set of open source tools effectively. Indeed, need to convert data in 3D tiles format are not always the same, as these usually depend on how source data have been collected, for example, and the process to follow is not always the same, and frequently it is not. And it depends also on the format. So for this reason, it is quite important to have the necessary instruments to be able to catch all these shades of gray in the process of converting the to 3D tiles, and so have necessary tools for visualizing, inspecting, and assessing input data sets, have the ability to manage and manipulate data sets for the desired, to reach the desired results. Yes, so let's think on the classification, the colorization, and so on. But be also able to manage reliable instruments to tune tiling options, coordinate the reference system, and all the other georeferential adjustments. Please, the next. So the main objectives, of course, are collect the best open source tools for the purpose, okay? So to process common data sources in the urban environment. That's the goal for us now. Shapefile and last files for now are supported. Provide, of course, workflows to orchestrate a set of processing chains and methodologies to expect, evaluate, prepare, convert, preview, and so on. And all of this having available an user-friendly UI to facilitate the work. So giving this overview, I think that we can now go more in depth with Stefano to learn how to use the digital twin toolbox with some example of use and learn more about this. Thank you so much.
Thanks, Tobia. I'm presenting myself. I'm Stefano Bovio, and I work at GeoSolutions on the projects like MapStore Core and the GeoNode front-end part as a front-end developer. And I helped with the team to work on the digital twin toolbox, this set of tools that will allow us to see today how to convert the data that we are before in 3D tiles for aiming to digital twin visualization. So this is the final result that we want to get at the end. So creating this subsample of the city of Washington, D.C. We downloaded the data and prepared some data, sample data that you can replicate that at the end of the webinar following also the recording. So the idea is to, based on open data, convert that in 3D tile data. So having this step from an open portal, obtain this data that we already prepared with a link that you can download. I will show how to process this data with the digital twin toolbox. And finally, I will present the visualization inside the MapStore WebGIS map view. The structure of the data that we will see and we will convert are focusing on three different main type of data. From the actual extension, shapefile or not, we selected some we think that are meaningful to the representation of the digital twin. So the buildings volume that usually can be reconstructed from a shapefile. So you have the building footprints, you want an extrusion, and then using this extrusion in your application. Trees. So here we will demonstrate how you can get an instance model for each tree that you have in your data set. And finally, the whole urban environment represented as a point cloud, so LAS, and how we can manage to process this data and convert it. To be already introduced the digital twin toolbox, I want just to highlight few things. First of all, it's a tool that is an ongoing work. This is not production ready, but already allows you to create on your own laptop, for example, using a Docker, the 3D tiles. And I will show this later, how it works. The reason also for 3D tiles that we are using 3D tiles, and here there is the links, are an open standard, OGC open standard. So this is another reason that we selected this format. And it's able also to streaming a massive 3D geospatial content. So these two parts are important for us to bring and work with this kind of format. And finally, at these 3 steps, that is the final visualization, we are using an embedded MapStore viewer. It's an open source WebGIS framework where we can visualize our output. So the digital twin toolbox setup. Digital twin toolbox you can find on the GitHub is hosted on GitHub in the repo under our GeoSolutions -IT organization. You can find the repo there. And before to start, you need some tools on your machine. First of all, you need Docker. So Docker open platform for the development. You can install both on Linux, Windows, or Mac. There are different ways to install it. Here there is the link to the quick start, and also Git. And here we are not using for the version control itself, but to clone the repo on our workspace on the computer. Here are the setup steps. So once you have this installed in a computer, you need to clone the repo in your workspace. So navigate in your workspace and run this command from a terminal. And this will create a new folder called Digital Twin Toolbox. Then go inside the Digital Twin Toolbox, copy the .env sample and create a new file called .env. Once everything has been done, you need to start and use the Docker Compose Up command from the same command line. So you are inside the Digital Twin Toolbox and use the Docker Compose Up. The first time that you will use the Docker Compose Up, this will also build one of the application inside the web app in particular. So it will take around 20 minutes. But the next time that you're using, it's already created the image for Docker, so it will be faster, the initialization. I will show after that. My machine here, I already prepared that, so we can go right away in the application. But these are the steps. Clone, navigate on the folder, copy and create a new .env file without changing everything. What you have inside the .env sample, it's already the default setup, and then start Docker Composer. Once you start, the application, it's this 3D space where you can navigate, and a control panel at the top here. So you can reach this to the localhost 3000. This is the default port, and it's running locally. It's running on localhost. And right now, it's the only way to start it. The user interface. There are 3 parts in the user interface. The first is the controls that are on the left. Here with the control, they change based on the input data. This input data can be shapefile, can be last file at the moment. And you can switch with a select, and the structure of this UI will change based on the input data, providing different action and variables to apply to the processes. The central part in the background, it's composed by a 3D viewer. It's used mainly to preview data that you want and to process to create the 3D tiles. So it's mainly a debug interface to have a quick feedback on the current structure or the geometry that then will become 3D tiles. Finally, we have on the left process feedback. It's logging all the background processes, all the interaction that we are doing with the action in the UI. It's mainly in this phase, in the initial phase of this work, it's really helpful to understand what's going on in the process if something's not working. And may have also additional debug view. Now that we see the user interface, I'll move away from the slides and I'll start to do a live demo of this work. Before to do that, I want just to introduce the main workflow that we will see. this diagram has two main, let's say, this directory. We starting always from a data directory, always going in a tile set directory in our workflow, and sometimes coming back to the data directory. So create a new input data from the data that we have already. There are three main processes. So the conversion of shapefiles, the processing of point cloud data. So let's say some adjustment of the point cloud. Sometimes as is not enough for the processing to point cloud. I will explain later the reason. So we need to process data and create a new last file as input data. And then we have the conversion of point cloud to 3D tiles. These three highlighted processes are the one that we will show today. We included also in this presentation an experimental conversion of LiDAR data to 3D mesh. So, but this is experimental because it's still an ongoing work. We want to highlight that there is also the idea to improve this part in our workflow. So this is the current solution that you find when you start the digital twin toolbox application. Before to start, I'm going to do this step and show you how to do. We have the sample data that can be downloaded from here. It's a zip folder that contains several data, and we need, before to start everything, to place this in the static folder. And I'm going to do that. So moving from here. So now here, as you can see, we have a digital twin toolbox directory, and you have something like this if you clone the repo as the setup step. So you run a git clone, GitHub geosolutions-it digital twin toolbox. Here you get a folder like this. And if you downloaded the sample data, you have a zip folder like this one. Just to show also another part of the setup, here in the file we have the .env and .env sample file that are at the same file. Just copy this file and rename it. So these two parts are important. Now we need to set up the data first of all to ensure that application is initialized correctly. And to do that, we need to unzip the content of this folder. So extract code. Extract in here. Now that we have the content, you will find inside a last file, a orthophoto, a TIFF file that it's as the same extension of the last file. So it's the same tile of the last file, and we'll use this for the colorization. Then we have a building, a footprint, join building 3D PSG 26985, that is the building footprints that we will use to create the building volumes. And finally, the trees as urban forestry. These are the files that we're using to construct the representation that we saw initially in the slides. I'm going to, first of all, we need to copy this, and I paste this here and this here. Go in the digital twin toolbox. The important folder that we need to pay attention is the static one. Static one contains in the data, the input data, and by default it's empty. So you need to copy this file here and moving there. So every time you need a new input file to add a new shape file or a new last file, you can drag and drop here. Important that the shape file should be inside a zip folder, and last file as is. Does not need a zip folder. Once this is done, means that the application will be initialized. You can also add when the new data when the application is already initialized, and then refresh the web page. So it's not important in this phase. I want just to start with the application with something inside. Then I will open a terminal. I'm using the WSL Linux subsystem. because I've Docker installed there. And I can use the Docker compose app command. So every time that you want to start the application, you can run the Docker compose app. This will start. There are right now 3 containers. One for the PostGIS that it's used from some processes, one for Nginx for the manage the endpoint, and the digital twin toolbox that it's the actual application that collect all the open source library that we found to generate these processes and convert to the 3D tiles. You will see if you're using the Docker Compose some feedback, and at the end you will see the listening on. It means that internally a start. So we can go in our web browser, open, and go to the HTTP localhost, not this one, but 3000. And you should see something like this if everything is working. You have the 3D background where you can use the left mouse and click and drag to run, and the right button of the mouse to rotate. So click, drag, keep mouse down of the right, and then you can rotate the view. And use the mouse wheel to zoom in and zoom out. So these are the interaction with the main view. Now it's empty because we did not select anything. We can start by the UI by selecting the first input the data that we want to convert. That is the building footprints. So here we select the building footprints. So the selection, you can choose the data that we included in the static data folder is there, so it's available. We have the name of the file plus the extension. Once we selected for some certain type, like the shapefile, right away it's creating the 3D view. As you can see, this file, it's composed by footprint of the buildings, but you can see that they are not flat, but some have, so the vertex of this shapefile have a Z coordinate, so they are located also in the 3rd dimension in the space, not just a flat footprint. That it's aligned with the actual terrain. Now that we have this data inside, the first thing that we may want to do to create a volume is to extrude this volume. And to do that, we have section in the control panel called geometry options. Here we have few options like lower limits, upper limits, height in meter. So we can decide to, for example, using constant value to extrude everything to the same elevation code. So here we can put everything to 0, and then here everything to 100. Apply, and as you can see, all the features are starting from 0 with the lower limits, and then the upper limit is to 100. This is just to show you that you can change this variable to have a preview. Here on the left, we have the logging of what's happening. Here it's telling us that the geometry is adjusted. And here, the result is not this one something that we want, because not all these building has the same height. So one thing that we can do with this UI is to use expression using properties for each feature. If you inspect this input data, this contains for each feature as information related to the minimum Z, maximum Z. So we can use this information to create the extrusion for each feature. For example, we can say the lower limit use the value, and the maximum is the max Z value. These are properties of each of these features. So if we apply, we get the extrusion with the correct height for each element. This could work, but we could improve also better with the option that we have with the digital twin toolbox. For example, we may have some differences in the Z value. In this case, the Z value here is evaluated above the C level, but instead, the geometry itself, it's an ellipsoidal geometry. So we can use a more advanced expression, like using a computation of the dollar mean Z. This dollar mean Z is taking the average, sorry, the minimum Z value of each features. And we can use this to extrude by using an expression more complex than the one that we have before. So taking the differences in between the max Z value minus the minimum Z value. In this case, we are computing the height of the volume, and we are starting this from the minimum Z value computed on the geometry. And without putting anything to the lower limit, the application itself is computing and keeping the lower limit by the default geometry and applying the upper limit from the formula that we use here. Now, this is just to showcase that you have several options based on the data that you have that you can use to create your volume. And the workflow behind is also able to detect if the lower limit is higher to the upper limit and swap is its name. Then once we are good to go with our geometry, so this is the volume that we want to represent our digital twin, we can pass to the next section, that is the tiling process. Here we have a few options. You can use the default one. I want just to highlight that you can decide how many features should be per tiles. Here by default we have 100. And you can adjust the geometric error. Geometric error is used in 3D to decide at which distance the application should display the content. So if we increase this like 500, means that we can see this far away. So this value could be adjusted also after some test in the final sample to see if it's working well for our purposes. So by default, we are keeping these 250 meters, but this could change. Once we are good to go, we can click on create file set, and this will initialize a process. This process uses PostGIS plus where we store the geometry, and it's using also the library called PG2-3DM. It's an open source library that starting from polyhedron stored in PostGIS, it's able to convert in 3D tiles. As you can see here, we have the feedback from the backend side as generated tiles. And we have a button here that allows us to have a preview of our tile set. If we click this open new windows, where we have our 3D tiles. And as you can see here, we have it's the same, so the geometry are following the same structure that we have here. And we can test also using the scroll down. As you can see now, is disappeared because it's to 250 is not. It's outside of that range, the camera, so it's hiding the value. It's a sort of computation of the pixel value of the error of the geometry, computed on the fly based on the camera position. Then we have also a possibility to have some option like the debugging of volume. Here it's creating some bounding box to highlight the tiles, so where the tile has been created. Now, this means that with these two steps, we created a 3D tiles for the building volumes. It's the first step. We can then move to the next input data. We are always working with, in this case, with the shapefile, but in this case, are points. Our points, so the workflow is slightly different because for each point, we should decide what kind of model we want to apply. In this case, we have trees. So we, at the end, want to have something that resembles a tree. So each of these model is a GLTF model, GLB in format GLB. And inside the application, you can find a static folder, a GLB folder here. So the model default is a cube, then you have a cone by default and a tree. So this one is the one available, but you can add additional model if you want. So you can create a model, for example, with Blender, and then add this to the folder. Here then we can decide to, so we have the preview, we see that the location, and here we may want to change the model, and we have some field in the geometry option in this case. There's no upper limits and lower limit anymore. We have model, rotation, scale, and translation. Now, for this use case, for this webinar, we have trees, so we want to use the tree model. So we just add in using the double quote, the string 3GLB that corresponds to the model that we have in the folder I showed before, so the GLB1. If you apply this now, it's importing that model, and we will see trees in this case. And all these support expressions. So for example, we know that there is the height value for each tree. We may want to scale this. For example, using height value, it's inside of each feature. We have this information we can apply. It probably is too much because the model is 10 times big. It's not value. Now this is not the current value because the height it's in feet, so we need to multiply for 3048 and then apply. So here we can see that we can also modify the shape, the scale of the model for each feature. Remember that when you decide this will be persisted in file view, you cannot change on the fly and in the file application. So it's something that it's then stored inside the 3D tile itself. For the moment, we can decide to keep just a marker, each of these elements. We can also work on the rotation. So if we have value that we want, property that represent a rotation, we use this for example, for a point of view. You can use the cone, rotate the cone based on the direction that you want to represent the view that we want to highlight. So once we have decided that the model is the model that we want, we passing to the next section here. We have the tiling option. Here we can decide the type and features, and as we have before, the maximum geometric error. So at which range we should stop to see the tile set. We can use the default one and create the tile set. Here it's using another library, using always PostGIS behind the name of the library. I don't want to say that wrong, so I go into it. So it's readym export. This is the pipeline of this process. And here at the end, we will get the same workflow as we have before with the tile set preview. We can click on this, and we have the preview as before. In this case, we have trees. The model, the original model, contains also colors. Add the colors. You can see no color here because here is a debugging view. This one, it's meant to show if the faces are visible with these colors. But at the end, in the final preview, here in the windows, here we can see the model. So In this case, we can see also and detect the tiles generated. Now the white color, it's not so visible, but when you are working on this, you can see the division of the tiling inside. And this is the workflow that's representing the points instances. So if you have a point shapefile, the one that we saw before, it was the polygon shapefile. And this was, we close the processing of polygon and point in shapefile. Now we can go to the point cloud here. So when we select the last file, we can see that there is no preview. The reason because we need to generate this preview. And we can do that with this section with visualization options here. We can click on create a data sample. At the first time, it will take a while, some few seconds. The next time, store this information, so it's faster. And here we have the sample of the. We're using this for debugging purposes and see if the point cloud is colorized, there is RGB information or. One thing to know about point cloud also is that in some cases we will need to adjust the vertical datum. This because in some cases like this one, the elevation is computed above the sea level, but the Cesium, that is the map engine that we are using, MapStore, is expecting the elevation above the ellipsoid. So we need to convert this point cloud and process this point cloud to generate another one that has two things: a correct shift of the elevation, and the second one is to have the colorized images. So we will use the process data here to generate this new point cloud that it's adjusted on the vertical datum and has colorized the first of all, we get also information about the projection that we can do from metadata that will be helpful later. When you click on projection, you get on the left the output. And here we need to, first of all, give a new name. So we create a new file called 1916 processed. Then we have to convert this. To do this, we need, and I'm going to show you the slide. Oh, not this one. Sorry, I'm here. So here we need for the vertical datum, we need a geoid information that we can download. Here there is a link on ProJ repo, and we can download and then place this inside the digital twin toolbox in vdatum, like GTX file here. So after you did that, you can, for this specific case, we know that the PSG is 26985. We are using this geoid as a starting point from this projection to the ellipsoid of 26985. So we need to copy this. And from CRS, so you can use a ProJ here and here to CRS. And finally, here on the raster image, we can use the image that it's inside, the TIFF image that it's inside the data that we provide the sample. So this processing will start a PDL pipeline. So we can start this. And here we can see in the meanwhile that we wait the result. So here we have from the data, we are getting the last file, the TIFF image for this orthophoto, using PDAL both, create a new point cloud that will then place inside the static data folder. Waiting for the process to complete. So here you can also open the Docker behind, see the logging of the actual command running, and the pipeline that it's running behind in the background. Let's see how it takes to compute these. And here it's highlighted also the JSON file created for this pipeline. You can see that it's using the colorization, using the TF image inside the folder. It's taking the last file as input. It's using the filter reprojection. So from in SRS, it's going to out SRS. And then it's processing to a new file called 196 processed. Once it's finished, the application will reload here. And we have a new file called processed here. We can select this because now we want to work for this for our 3D tiles, and we can create the preview. Sample preview here. Now we can see we have the same point cloud, but it's used the orthophoto and apply the colorization. We cannot see the datum shift here, but also that has changed. Now with this, we can not use the process data, but instead skip to the next step, that it's the tiling option. Here we have few options. The one for the CRS number wants just the authority number here. We can use the one that we detected before, the 26985. 26985. And then there is a geometric factor that it's used to adjust the geometric error. For these tiles, for example, we are using a 0.115, but this needs to be adjusted based on the use case. When we have this done, we can create a tileset with the tileset button here. Deal with initialize a new process. In this case, it's using another library. As you can see, we are using different library based on the input data. In this case, we're using the Py 3D tiles library, a Python library, as a command line behind that it's running. Here we have the feedback of the current state. Let's wait a few seconds on the. And here we can see that the logging here is taking information, some of the information that we get from the backend, just to have a quick idea on what's happening behind. Now that we have 100%, it will take also a few seconds to generate the setup, modify if it's needed the scale of the geometric error. And we expect to get a tileset preview as we had before. Let's wait a few seconds.
Hey, Stefano, real quick, while we're waiting on that, I
Yes.
do want to emphasize, if anybody has any questions, go ahead and post those to the Q&A section. It should be at the bottom of your Zoom window, and we'll be happy to answer those. We'll go through those at the end of the session.
Now that it's completed, we have the tileset preview as we had before. We can click on this and get the view of the point cloud. One thing that I mentioned, that if the point cloud contains the classification, this process will keep the classification information inside. We have a button here to test this, that it's going classification, that it, toggle, and we can see that the color is applied. So this is the final 3D tiles that we generate. We can also debug as before the tiles to see the structure and see if it's optimal for our view. disclose the three processes that we want to present as live preview. That is the complete set of these three elements that could represent the digital twin model. Going back to the presentation, just quick on the few information about the ongoing work. So we have the experimental also for the meshes that you can create mesh from point clouds. And here we are using Blender, but it's still an ongoing work. Here are the results that we get. So if you initialize the process from the point cloud to create a mesh, then you can use the PLI file that you have inside to test this. It's still not optimal solution because there are issues on the reconstruction on the vertical surface, and some edits take a while to generate, almost 30 minutes to generate the tile set. So I cannot showcase this today, but it's available there. And within the slide, you can follow the step to cover and complete this. To complete this use case for the city of Washington D.C, this sample data, you can all preview the data directly using the tileset previewer that we saw before. All the tilesets are included in the static tileset folder, so you can copy and host whatever you want the output. Or there is this option available at the top. You can check the tileset that you want, and then show the results inside the MapStore viewer. Here is the result. So you can see that inside the MapStore, you can view all the tileset together. And the MapStore here, we can showcase that include some option. For example, ability to increase the size of the points, the style of the points, style of each feature inside, and also query the element. So the information that was inside the shapefile at the end are also inside the 3D model. So we can use that to the 3D tiles and the 3D model inside. So we can use that to query, but also to apply style specific to elements. Also for the points, we can classify based on a value, property. Finally, we can use the tool that MapStore provides, such as the measurement tool and map views that are not included in the default one. But if you want, you're interested on the project MapStore, we left here some links on the latest releases and on the repo and documentation. So you can take a look also at the project MapStore itself. You can use the output of these processes inside MapStore. Now I'll let my colleague Georgios talk about.
Thank you so much, Stefano, for your presentation. I would like just to take this opportunity to say that that we are still actively working on this. That as specified by Stefano Bovio, it is not production ready yet, but pretty much already functional. There are some important aspects anyway we are working on. And one of them is the adding of point cloud capabilities, point cloud classification capabilities. So for this, effectively, I would like to leave the talk to Georgios Petrakis, who is actively working on the task to provide a taste of incoming new features you will see for the digital twin toolbox. Thank you so much.
Thank you, Tobia. Thank you, Stefano. Hello from me too. I'm George Petrakis. I'm working on geosolutions as a software developer. My background is related with web-based GIS development and artificial intelligence. And in this presentation, I will present you an investigation that we're conducting for point cloud classification as an ongoing work for the digital twin toolbox. Next slide, please. But at first, what is point cloud classification? Point cloud classification is the process of assigning labels to individual points in order to identify and categorize different objects or features in the point cloud. For instance, in this slide, on the left column, we can see the original point clouds, while on the right, you can see the corresponding classified point clouds. As you can see, the buildings are displayed in red, the vegetation in green, the road network in gray, and the ground in yellow. Each feature is presented in a specific class. Next, please. But why point cloud is important? Point cloud classification is a significant part in data interpretation, since it accelerates the data analysis. It provides crucial information about the land cover and land uses. It's important for an algorithm or a system to be aware about the semantic features of the scene. In other words, to know which label or class belongs to which point. Moreover, beyond the 3D urban reconstruction, it can be used in various applications, including self-driving cars, inspection, autonomous navigation, and so on. But here in this project, we focus on urban point cloud classification. Next, please. And now let's talk about the ways that we have to classify point clouds. The first and easiest but time-consuming method is to classify a point cloud by selecting every feature in the point cloud or dataset manually and assign it with a label, for example, a tree or a building. To be more specific, a user is able to classify a point cloud, creating the outline of its feature using an external software, let's say. Although this manual way is quite time consuming, it's still used for the training data generation, the training dataset generation, because the learning-based algorithms are able to learn using both the original datasets and the corresponding ground truth, which is the assigned labels of the dataset features. Developers and computer scientists trying to find a more automatic approach initially tried to automate the point cloud process, designing deterministic scripts, which included several rules and statements. For example, if a rule could be if you find a feature with this color and this geometric shape, assign it as a tree. However, this approach was not effective in different scenes. Subsequently, with the advent of artificial intelligence, several machine learning algorithms such as support vector machines or random forest and deep learning architectures such as PointNet were used on point cloud classification and outperforming the handcrafted algorithms. The general idea of the AI-based algorithms is the use of multiple samples or training data, as called in deep learning terminology, where, as I mentioned above, it includes the original data and the corresponding labels or ground truth in order to learn how to recognize these labels. After the learning process, the AI model should recognize the labels that has learned in a known for the dataset for the model datasets. It's important to note that the efficiency of the AI model is highly dependent of the training dataset. To give a simple example, if a model is trained to predict features in an indoor environment, such as tables or TV or computers and so on, it will not provide accurate results if it tries to predict outdoor features such as cars or trees. Next, please. So in our case, we performed several experiments in outdoor environments, testing several AI algorithms, including machine learning and deep learning approaches. In this figure, the experimentation pipeline is presented. Initially, we have to prepare the data set in order to have a balanced data set in terms of classes and heterogeneity. And then parameterization is conducted, which is an important part in order to fine-tune the training process and export a refined result. Afterwards, we generate the model through the training process, while at the end, we have to evaluate the model using unknown for the model datasets. While, moreover, if we have generated more than one models, we proceed comparing the old models with the new one. Next, please. And this is a result from a pre-trained model focused on sparsely populated areas, including parks and villages, and not on urban scenes. While it was trained in order to recognize the classes ground, buildings, vegetation, and vehicles. On the right, you can see the prediction of the model in a sparsely populated scene with buildings, as you can see in the slide, with buildings in orange, vegetation in green, cars in yellow, and ground in gray. As you can see, the result is quite accurate. Next, please. However, in this slide, the model fails to predict a densely urban scene, since it predicts almost all the scene as buildings, because buildings are presented as with the orange color. However, this is a reasonable result, since this model was trained using sparsely populated areas. Next slide, please. Thus, we experimented with a model generation focused on densely urban scenes, including several experiments with different datasets, classes, algorithms, and parameterization. Here we can see one of our experiments in which we trained the model focused on urban areas using the Washington D.C. Open Dataset, while the classes that were used are vegetation, buildings, ground, and water. The parameters were tuned in order to find a balance between the accuracy and the complexity of the model, because we wanted an accurate but also a lightweight model. And next, please. Here we can see two predictions from quite densely urban scenes, with buildings in dark orange, vegetation in light orange, and ground in green. The result is much clearer and more accurate than the one by the previous model. If you remember the slide from the previous slide from the previous model. Next, please. Also in this slide, we can see two sophisticated predictions in sparsely urban areas with buildings in dark orange, vegetation in light orange, ground in green, and water in gray. Again, the result it is quite accurate. Sorry. Next, please. And in this slide, you can see the predictions of the model in a completely different data set from another city, another country, and which is completely unknown for the model, with more sophisticated content, since the point cloud displays an urban area in a smaller scale. On the left, you can see the ground truth of the point clouds, and on the right, the model prediction with a different color map. Next, please. Also, we tested the classification results on digital twin toolbox, and on this slide, you can see, as you can see in this slide, the user is able to see the classification results by selecting the classification checkbox on the right panel. So in a future version of digital toolbox, the user will be able to automatically classify a point cloud in order to further analyze and process the point cloud. And I think that's all for me. Thank you for your attention.
Yes. Thank you so much, Georgios.
Thank you.
Yes, I'm sorry. I would like to spend a few words on the future work. So stuff we are working on at the moment. So in sparse order, basically, not so sparse. I mean, we are talking about significant functionalities, improvements, and new capabilities for our digital twin toolbox. The first one is, of course, the one related to the classification, to the hardening of the classification capabilities of point cloud, including also, improvement on the user interface for managing this from the control panel. And the other stuff really important we would like to work on is effectively the ability to improve. Is effectively to enhance the ability to convert the capabilities. Sorry, to convert to generate meshes from point cloud. Okay. Of course, the intention is to work on other, on other kind of improvements and parts aimed at effectively enriching and improving the performances also, okay, of the final 3D tile generated from the digital toolbox, like the level of details and the tiling system and stuff like that, that are effectively already working well, but that can be for sure improved further. And of course, a kind of automation is something that we would like to achieve in the near future, in order to possibly automate what is currently need to be done manually entirely through the user interface or from command line. That's basically all. And before switching to the Q&A, I would like to also take the opportunity to thank you, the municipality of Genoa and Florence, who contributed basically during the last years also in the realization of the digital twin toolbox, or at least part of its functionalities, as well as many other MapStore capabilities for D3D. Regarding the digital twin toolbox, you can see here some online resources we put on the slides, some useful links. So for sure, the link to the project hosted in GitHub, where we have recently released a pre-release with the current functionalities that you have seen during this webinar, as well as a wiki page with a good description of available functionalities, configuration properties, usable from the control panel, and the concept behind, as well as some tutorials using same data you have seen in the webinar today, that you can follow also later on. Also following the looking at the wiki pages. So that's basically all, I think. Ryan, I think we can switch to the Q&A session.
Great, thanks, Tobias. No, go ahead.
Yeah, we have some questions, Stefano, here. Let's proceed in order, So is it possible that the recording and sample data of the webinar will be able after the, yes, basically the material will be, is available in the wiki for sure, okay? And the recording will be available online and for sure sent on everyone registered at the webinar, okay?
Yeah, it's in the wiki. You can find the same tutorial that you saw in the, if you want to don't wait to the recording here, there are the same processes that we saw.
Yeah.
Yeah, and you have the link here with the dataset you can download to test it.
Okay, so
Yes,
basically,
yep. If I can add real quick, also, if you go to GeoSolutions group in YouTube, you'll see the video from today posted there, as well as all of our previous videos as well.
good. So let's jump to the other. Can we use different 3D models for different tree types based on the attribute? I think you can answer to this, Stefan.
Yes, I will try to show. Now I don't have model here, but you can see the UI. I'm going for a moment to open this. I need the information. I'm using MapStore to get information, so I can show also this part. And probably this could be an announcement also in this UI. Here we have the same dataset here. Let's assume that we have a property that represents the name of the model. Now I'm using, for example, genus name. It will not work here because I don't have enough, but to show you that it's looking, I can use genus name plus .glb. So it's looking now for in the folder. If I apply, it's not able because it's not finding the name. So the name of the get value does not exist. So it's possible. Let me remove for a moment here. So the name must be something inside the property because it does not exist, these properties, and it's not possible to find now. But if it's included inside the data, it's possible to use that and get different model. That's it. So you need to have a field that has the model value inside. Next question.
Yes, sorry. So hello, is there a way to add WMTS styles from GeoServer to GeoNode using manage.py update layers? It's only adding WFS layer at the moment.
This one related WMTS layers. Unfortunately, now I don't have this information because it's really specific to GeoNode backend side. And
yeah, and in any case, consider even if we cannot provide all information now, since some of them may require some more time to answer. I mean, consider that you can use the official channels. I mean, also GitHub opening issues and things like that for your questions. Okay, thank you so much.
I want to go back a moment because before I wrote the wrong name here for the trees. If you get the correct, because it was uppercase, not lowercase. If you get the correct, it's looking inside for the name of the properties .glb, but these are not included in the static GLB. So if you add a model for each value that you want to create and you associate it to a point, like a category, you can use this. And we look and create a name of the property. You can plus a string that .glb and add a new model inside the GLB folder. Just to complete the answer before.
Thank you so much, Stefano. The other question, hello, thank you very much for the presentation. Thank you too. I would like to ask one, is there a way one can attach metadata on the 3D tiles using the toolbox? I will say the answer probably is not. I mean, I don't know. I don't know if there is some trick for this, Stefano.
Right now,
I'm probably not aware.
Right now, the only information that we maintain from a shapefile is the properties of each feature.
Yeah, the native properties they have.
Yeah, and from the point cloud, the classification if it's included. So that's for the moment.
Second question of the same participant. Could you provide a way to use the 3D tiles on GeoNode 4.3 or MapStore? I meant like 3D tile server. 3D tiles are already supported in MapStore for visualization purposes. Okay, so as a client, okay, of 3D tiles. For visualizing it, you can visualize them in MapStore. We are working on including, 3D tile support in GeoNode 2. It will be available in the next major release. So next question, do you tie large surface point cloud data in a manner similar to 3D tiles? If so, what format is used? And are there any open source tools available for tiling? I don't know if you want to answer to this. Stefano?
So for larger surface point cloud data, yeah, the approach is always to have tiled data because it's difficult to manage. Also to work in parallel with multiple tile, it's easier. But at the moment we test just LAS and LATS format. And the tools that we tried to split data was PDAL. PDAL contains also the possibility to split data, so we use that to make some tests.
Yeah, that is effectively. I'm sorry, please conclude.
Also, this part, as to be mentioned before, there is this ongoing work on the automation and including also batch processing. Now you saw a focus on a single element at the time, but the idea is this becomes like tuning of a property for a part of a bigger model that then could be automated in a batch process. So the way that we split for the moment in our previous test was PDAL for splitting and using LAS or LATS format.
Good. So in urban digital twin examples using open source tool, the focus has predominantly been on representing structures using ellipsoidal 8. However, is there a method to display this dataset above the terrain surface? Specifically, is there a clamp to ground function available, or are there any workaround to achieve this? I would answer that. That's capability is provided on the MapStore side. As a
one thing.
Please?
This I think it's related to 3D tiles.
Oh, okay.
Because
okay, probably
because
misunderstood.
it's not some vector data. If it's related to 3D tiles, if you are talking about like a geotiff that represents a terrain and then clamp the value and then create the point cloud. The point cloud, the 3D tiles. At the moment in the pipeline, there's no results on. So you need to provide already shapefile that has the correct Z that you expect to have on the surface, because the process here is just converting data to be then be a 3D tiles. On the point cloud side, we included the possibility to use a geoid to shift the vertical datum, but that's just the only part that we have. We don't have an option to say, get this terrain and use that at the moment, and use that to adjust the position of the, for example, shapefile that you can include. But it could be something that we can think on the announcement part.
Thank you so much. Next question. Are there any major consideration to be had when creating this kind of 3D layers on the topic of performance, not only for the machine used for processing, but mostly taking into account publishing said layers in MapStore Map, which may be viewed by a variety of people with lower and personal computers? Yeah, there are effectively performance improvements, some of them are already available. So tiling, pyramid optimization, lots, as I said before, geometric errors. For performing, the way the 3D tiles is visualized. Of course, there are also some trick on the MapStore side in order to improve the performances on the visualization. we are anyway still working on this, as previously said by Stefano, here and there for certain specific functions and optimization aspects. Of course, the 3D still requires, from a generic point of view, still requires more system resources than for the 2D map views, of course. I don't know if you would like to add something on this.
I can add something on the generation tile side. We are testing a lot on the option that are providing this open source library that we are using. One thing that we could suggest is to play a bit with the geometric error of the tile set. So decide when you want to display the content.
Exactly.
So lower means that you will be far away, the tile set will disappear, and maybe this could improve the performance. And also the feature per tiles, in particular for the shapefile processing. These two may help you to improve the visualization. It depends a lot on the size of the extension of the data that you want to cover. That probably could change the approach. One of the future work was also to add the possibility to have loads, but it's not included right now here. That could help
Exactly.
having this generalization of 3D geometry could help this process, but it's not, unfortunately, yet in our toolbox.
Yeah, but it will be available for sure for Wardle and next releases. I mean, that's effectively one of the main topics we are working on at the moment. Or anyway, we have planned for this. Okay, so next, hello, thank you for the webinar. Thank you. I'm interested in knowing if it is possible and supported to display 3D tiles point cloud below the terrain in MapStore. I mean, I will simply answer this, then maybe you can add something more. Of course, it is something that you may where you may have to pay attention on the generation of the 3D tiles. Basically, I think the vertical datum is here. Applying the vertical datum here is quite a relevant point. Of course, in MapStore there are also other options in the styling. In the styling panel, but also in the layer properties panel, where you can configure offset. You can offset basically your data in order to move it to offset it vertically. So that's something that I can say. Of course, I don't know if you have maybe something more to say about this, Stefano.
Maybe one thing that was in plan, something that we discussed, is the movement of camera underground.
Yes, of course. Yes.
And that part, so in MapStore, with the map views, we already integrated the fact that you can clip the ground, so you can place something underground.
Yes.
So that part is there, probably an improvement on the camera.
Yeah,
would help
you
more
are right.
the navigation.
Yeah, you are right. Of course, good point. It is, of course, possible to see underground data, in our opinion, and it is something we have discussed indeed recently. We should work on on improving effectively the way underground data can be navigated. Okay. So that's, of course, a good improvement for the future. Bravo, thank you. Thank you, very instructive. Waiting for the next session. Thank you so much. Is it LiDAR point cloud or photogrammetry? Maybe you want to answer to this, Stefano?
What you see today was an airborne LiDAR. We took it from the Washington D.C. For the moment, the photogrammetry is not implemented. It's one part of the future work.
Using this, it is possible to make building models like BIM model?
We work at something not like 3D tiles, because when we are talking about BIM, I'm thinking about the IFC format. For the IFC format, we directly add the support on the store side, so you can add a model directly there if you're interested to test it. In the digital twin toolbox right now, it's not possible to import this kind of data IFC, but it could be an interesting improvement as input data an IFC and convert that into 3D tiles. So not at the moment, but we can note that as an improvement.
Good, thank you. Next question, can you show some example of the attributes for the building footprints? I'm not sure I understood the question.
If you mean here the lower upper limits, when I'm using the, let me open building here, just to explain better what happened before. So we have these buildings. Now, if you click one of these buildings, we have information of each of these. And the min z, max z was inside each feature. So when we were applied here attributes, so min z, low upper, like max z is an expression, for example, multiply by 10 and then apply, we are modifying the properties. So here is an expression. This value is per each, and these are attributes of the buildings. So we are using.
Good. Thank you. How accurate it will be with respect to geodetic datum?
It's difficult to answer to this question because right now we are using a geodetic datum. The shift that vertical datum shift that we saw before, it's using a global datum. Most of these LiDAR sometimes come from a local datum that it's also difficult to access. I think if you get the same, if you get the LiDAR already ellipsoidal, that should be the default one. That should work right away. You don't need to pre-process that. If you want then convert with the geoid, you will need to find the most precise geoid to apply the conversion. So it depends a lot on that part.
Thank you. The next question is, if we have two different data of the same location, representing the same location from different time period, is it possible to overlay them to update the digital twin?
Well, I think it's like to create two models and two 3D tiles models and include like in a viewer like MapStore.
Yeah, I think that's yes, effectively.
Because the styling allows you also to, I don't know if it's a more like a visualization what you are referring to, because the styling itself allows to change also the opacity. So if you want to have a comparison, you can change the opacity of the element and see two different states.
Part. Yeah. Okay, good. Thanks for sharing your knowledge. The question is, are you defining digital twins as 3D models? What approaches you will use for syncing virtual world and physical world? Yeah, that's effectively a good question. Stefano?
Yeah, I think that today we just showed the structure of the digital model, so we can represent that model. So it was more focused on representation rather on the data itself. So we were thinking about sensor data that should be updated. Is open, a new webinar probably.
Yeah, that's an open topic basically, yes.
Yeah, because the digital twin is composed from different aspects, not just the model itself, and in this presentation, we focus mainly on this part.
On this part, exactly. Thank you so much to both. Thank you very much for the presentation and for the answers. Thank you too, of course. And thank you to all the participants for joining this webinar for the Digital Twin Toolbox. I think we have done. There are no more questions.
All right. Thank you, everyone. Thank you very much for attending. Thank you to Tobia, Georgios, and Stefano for your expertise and providing us with the demonstration. I do want to emphasize, if you have follow-up questions, you can either go through the community support pages for MapStore, not only MapStore, but GeoServer, GeoNode as well. And you can also email us at info@geosolutionsgroup.com. Thanks again, everyone, for joining. Again, stay tuned on our YouTube channel for this and all of our previous webinars, our blog as well, and we look forward to seeing you at the next GeoSolutions webinar.
Okay. Thank you, everyone. Bye-bye. Stay well.
Bye.
Thank you. Bye.